Hello students, today we will be learning one topic under semiconducting materials, that is carrier concentration in N-type semiconductors. I am Dr. Priya, Professor of Physics, RMD Engineering College. So, in general, first of all, we will know what is extrinsic semiconductors. We know what is an intrinsic semiconductor already. Intrinsic is a pure form of semiconductor. Extrinsic semiconductors are formed after the doping process is done. Now, there are two types of dopants. One is donors, the other one is acceptors. So, if I include donor type of impurity, then I get N-type semiconductors. If I include acceptor type of impurity, I get P-type semiconductors. The energy band diagram of N-type semiconductor and P-type semiconductors are shown in the picture. And here, in specific, the bonding picture in N-type semiconductor is shown. So the examples for dopant can be arsenic, phosphorus, antimony, etc. So here I am showing phosphorus. So which is a pentavalent impurity. So 4 of its outermost electrons are involved in the formation of covalent bond with its neighboring Si atoms. 5th one is free to move. So every dopant, that is every donor impurity which is added into the system is responsible for giving out one free electron. So what happens? Totally large number of free electrons are accumulated, making free electrons or electrons to be majority carriers and holes to be minority carriers. As you all know, in semiconductors there are two types of charge carriers. One is electrons, the other one is holes. So because of the donor type of impurity, that is pentavalent impurity, you are able to generate one free electron per every impurity atom. So making electrons to be large in number, making it to be a majority carrier. Now coming once again to the energy band diagram. Let us discuss about a P-type later. Now we will talk only about the N-type semiconductor. So this dopants are added into the system, no? So these will go and occupy a place near to the conduction band. So all the donor impurities will get settled here. And the band gap is between conduction band and the valence band. Rest of the details, as we do the derivation, you will understand. So let us start the derivation. Carrier concentration in N-type semiconductors. So we know N-type semiconductors are formed because of the pentavalent impurity, and because of the pentavalent impurity you are able to get one donor level, and this donor level will lie close to conduction band. Okay, so a small disturbance is enough for this level to immediately donate the electrons into the conduction band. So the electrons will immediately jump from donor level into the conduction band, making large number of electrons to be available in the system. So this is the energy band diagram. So the starting point of this derivation will be what we have done in intrinsic carrier concentration. That is, we have calculated the concentration of electrons in the conduction band. So let us take that as the starting point and then proceed further. Let me write that equation. Ne is equal to 2 into 2 pi me star kBT divided by h square whole power 3 by 2 exponential EF minus EC by kBT. Please do along with me. Now I have to find out the carrier concentration. Okay, which means I have to find out the majority carrier concentration, that is the electrons. Now you see here there are fully electrons available in this level. Now the smallest disturbance is sufficient for the electrons to jump into the conduction band. So now if I try to find out the concentration of electrons from the conduction band, we will definitely not know whether it was already available in the intrinsic form or it is donated by the donor level. We do not know. We cannot find out at all. So what is the contribution given by this cannot be understood at all. So it is very difficult to find out the carrier concentration of electrons. So instead what I can do is, in the donor level, after the electrons are jumping into the conduction band, holes are going to be created, is it not? So if I find out the concentration of the holes, it is nothing but the same electrons have gone into the conduction band. So instead of finding out the total number of electrons, I will be finding out total number of holes. Okay, so let us assume ND to represent the number of donor energy levels per centimeter cube, that is per unit volume. Then what else have to be assumed? Z of ED, and to represent the density of energy states which has energy ED below the conduction band. Okay. Now I will write the equation like this. N of ED dE is equal to Z of ED dE. After that what should come? Fermi function has to come. Now first of all, what is this? This represents density of holes in the donor level, as I told you. Okay, density of holes in the donor level is N of ED dE. Now that is nothing but density of energy states in the donor level, that is Z of ED dE multiplied by Fermi function. Now I am talking about holes, not electrons. So I can write that as 1 minus F of ED. Okay, all these things you know already. So this N of ED dE, I can write it as NH. Okay, it is nothing but holes. Then Z of ED dE is nothing but ND, just now we have told, into 1 minus F of ED. Okay, so I will number this equation as 1 and this equation as 2. Now let us simplify this one. We know what is F of ED. So I will write 1 minus F of ED is equal to 1 minus 1 by 1 plus exponential E minus EF by KBT. So what can I do? I can take the LCM. 1 plus exponential E minus EF by KBT. 1 plus exponential E minus EF by KBT minus 1. So this 1 minus 1 gets cancelled. Now look at this expression. So we know the scale of this energy band diagram is something like this. We have seen that already. So the energy band diagram starts from minus infinity, it goes up to plus infinity. Now you can understand E minus EF. You know, E is some energy present inside the donor level. So I will write this as ED. Okay, that will be the appropriate way of writing. Okay, so this ED minus EF. You can see in the picture, ED is here, EF is here. So is it positive or negative? It is negative. So ED minus EF is negative. Since ED minus EF is negative, what will I get? Exponential of ED minus EF by KBT will be what? Much lesser than 1. So what I can do? I can ignore this term, so that 1 plus exponential ED minus EF by KBT will be approximately equal to 1. This is something like this. Say 1 plus 0.0001. It will not make a big difference. So I can simply approximate it to be equal to 1. So this is equation 3. So now because of this approximation, what happens to this equation? In the denominator, it will become simply 1. Only the numerator remains. Okay, so 1 minus f of ED is nothing but exponential ED minus EF by KBT. Let us write that. 1 minus f of ED is nothing but exponential ED minus EF by KBT. So equation number 4. Now I will substitute 4 in 2. So I will get NH is equal to ND into exponential ED minus EF by KBT. Equation 5. Now you have to imagine the situation correctly. See, from the donor level, the electrons are jumping into the conduction band. Now you cannot resist from the conduction band electrons falling down also. So there will be a quick transition of electron movement from either from donor level to conduction band or from conduction band to donor level. So both will continuously take place. So there will be a stage called equilibrium when this will be almost equal. What will be equal? Number of electrons per unit volume in conduction band will be equal to number of holes per unit volume in the donor level. So at thermal equilibrium that will take place. So let us write that at equilibrium. So always we consider equilibrium to be the state of measurement only because of that. So all this rough movement will all get settled at the stage of equilibrium. Then it will be, the system will be suitable for any measurement. Before that, if you take, means the measurement may not be accurate. It may not be standard. Okay, so this is Ne, that is the number of electrons per unit volume in conduction band, is equal to number of holes per unit volume in the valence band. So that is equal to NH. So I can write the equation now. You look at the first equation and write down for left hand side 2 into 2 pi me star kBt divided by h square whole power 3 by 2 exponential EF minus EC divided by KBT is equal to ND. Look at the fifth equation, that is NH. Exponential ED minus EF by KBT. Now simplification only. From here it is simplification. So if you write the fundamental equations, that is carrier concentration means density of energy states multiplied by the Fermi function. So if you are able to rightly define the number of energy states in the donor level, so you do not know how much it is because it depends from system to system, it is going to vary. So I am simply taking it to be ND. Okay, then F of E represents normally the probability of finding an electron. Here I am going to find out the probability of holes. So 1 minus F of E. If you frame that equation correctly, thereafter it is a monotonous way of doing only. It is, you will not go wrong at all. Okay, so continue. So I will bring all the exponential terms to one side. So exponential, the denominators are same. So KBT, EF minus EC minus ED plus EF is equal to ND divided by 2 into 2 pi ME star KBT divided by H square whole power 3 by 2. Now you can see here exponential 2EF minus EC minus ED divided by KBT is equal to ND into 2 into 2 pi ME star KBT by H square whole power 3 by 2. Now I will first find out what is EF. Okay, this EF has to be substituted in the first equation to get the carrier concentration of N-type semiconductor, that is majority carrier concentration. Okay, so I have to bring out an equation for EF, means you should see here that it is inside the exponential. So what should I do? I should take ln. So taking ln on both sides. I will write down here. Taking ln on both sides. 2EF minus EC minus ED divided by KBT is equal to ln ND divided by 2 into 2 pi ME star KBT divided by H square whole power 3 by 2. So I will have to now retain EF. So for that I will split this term and write as 2EF by KBT minus of EC plus ED by KBT, of course with a bracket, is equal to ln of the same term. Okay, I will continue in the next slide now. So let us now write the expression for EF. EF is equal to, I will write the equation directly, EC plus ED by 2 plus KBT divided by 2 ln ND divided by 2 into 2 pi ME star KBT divided by H square whole power 3 by 2. Okay, now this is the equation for Fermi energy for any temperature. Now I have to locate this Fermi energy in the energy band diagram. So let us draw the energy band diagram and try to understand where we find it difficult. Okay. So energy band diagram starts from minus infinity, it goes up to plus infinity. Now we are in n-type semiconductor. So majority carriers is electrons that will be present in the conduction band. So wider conduction band and smaller valence band. So this is my valence band and this is my conduction band. So I indicate the lowest level of conduction band to be EC and highest level of valence band to be EV. Now I am using dopants, that is donor type of impurity. So that will occupy very close to EC. So I name that as ED, which will have several electrons. Now instead of counting the number of electrons, I am going to count the empty donors. That means holes in the donor level. That is how I am doing. Okay, so just to show my understanding, I am showing this transition also. Now we have to locate this EF. So for that what I do is I assume temperature to be 0 Kelvin. So what will happen to my EF equation? Simply EC plus ED divided by 2. So EC plus ED divided by 2 means exactly halfway between EC and ED. EF. So this is how we locate. Now you can ask a question, now what will happen if I raise the temperature? So when I raise the temperature, what will happen? More number of electrons will jump from ED and into the conduction band. So when more number of electrons are added, what will happen to conduction band? This plus infinity will not become plus plus infinity. So what will happen means EC will come down. So when EC is coming down and also one after the other ED is, see this is a band of energy level, okay, something like this. So after first energy level, next. So it moves like that. So what happens is ED will also come down. So EC coming down and ED coming down and EF will have to come down. No other choice. Okay, so to make itself available between EC and ED, EF has to come down. Okay, now I keep on increasing temperature. Large number of electrons are getting transferred from donor level into conduction band. So how long this will take place? Can it go endlessly? Can this shift of EF will keep continuing down? Means it can continue so long as it is not touching the intrinsic Fermi energy level. Where will the intrinsic Fermi energy level will be? Between EC and EV halfway through. Okay, so roughly I just change the color. And show you like this. Okay, this is EFI. So intrinsic Fermi level. So this EF will keep coming down till it reaches EFI. Only that is the maximum possibility limit. So the movement is one step down like this. Okay, it is not the way it is shown. Okay, it is coming in the vertical manner, one after the other. Okay, it will reach EFI, that is the maximum. Beyond that, if you increase the temperature, what will happen means the material will lose its semiconducting property and overlapping of valence band and conduction band will take place, which means the material will become a conducting material. So it will go to that stage. Okay, so let us name this as A and continue with our derivation. So this is about the energy band diagram. Now my target is to find out the carrier concentration. but I have not yet found. I have found only the Fermi energy. Now I have to substitute this Fermi energy in the first equation. Only then I will be getting the carrier concentration. So what is that first equation? Ne is equal to 2 into 2 pi me star kBt divided by h square whole power 3 by 2 exponential. What is there? You just look into it. What is given in that is EF minus EC divided by KT. Clear? So, in the place of EF, I will have to substitute equation A. So, EC plus ED divided by 2 plus KBT divided by 2 ln ND divided by 2 into 2 pi me star kBt divided by h square whole power 3 by 2 minus EC whole divided by kBt. So this is the equation. Okay. Now after this only simplification. So how to simplify? First let us take this denominator kBt above. Okay, so 2 into 2 pi me star kBt divided by h square whole power 3 by 2 exponential EC plus ED divided by 2 kBt plus, if I bring it up, this kBt and this kBt gets cancelled. I will have 1 by 2 ln ND divided by 2 into 2 pi me star kBt divided by h square whole power 3 by 2 minus EC divided by kBt. Now you can simplify this term and this term. You can see here, you can take the LCM 2 into 2 pi me star kBt divided by h square whole power 3 by 2 exponential. I take 2 kBt common, not common, LCM, EC plus ED here minus 2 EC. Then plus ln, I will take this half as power. Okay. So ND by 2 into 2 pi me star kBt divided by h square whole power 3 by 2 whole power 1 by 2. The entire thing is inside the exponential. Okay. So I will get now ED minus EC divided by 2 kBt. Then plus ln this term. Okay. So 2 into 2 pi me star kBt divided by h square whole power 3 by 2. What will I get? Exponential ED minus EC divided by 2 kBt plus ln ND divided by 2 into 2 pi me star kBt divided by h square whole power 3 by 2 whole power 1 by 2. So exponential of this term then multiplied by exponential of next term. See, Exponential a plus b is nothing but e power a into e power b. So apply that. What will I get? 2 into 2 pi me star kbt divided by h square whole power 3 by 2 exponential ed minus ec divided by 2 kbt into exponential and ln will get cancelled. So nd power half, I am just bringing this power also inside. So 2 power half 2 pi me star kbt divided by h square whole power 3 by 4. Now you can see this one and this one gets cancelled and it will become 2 power half. Similarly, this whole term and this will get cancelled and this power will become 3 by 4. So I can now write the final equation. Ne is equal to 2 power half 2 pi me star kbt divided by h square whole power 3 by 4 exponential ed minus ec divided by 2 kbt. So this is the carrier concentration in an n-type semiconductor. So here this in the energy band diagram, the energy difference between the donor level and the conduction level will be, that is EC minus ED will be nothing but ionization energy delta E. So this is called ionization energy. So I can write this expression. Where is ND? I have missed ND, no? So ND power half. So I can now write the above equation as like this. So 2ND whole power 1 by 2 2 pi me star kbt divided by h square whole power 3 by 4 exponential ed minus ec divided by 2 kbt. So this is the, sorry, we wanted to change this, no, as what? Minus delta E. Okay, so this is the final expression for carrier concentration in an n-type semiconductor. Okay, this is one very important question, examination point of view. You should know the final expression also by heart. Okay, sometimes the final expression alone can be useful for solving the problem, as well as the final expression alone can be asked as a part A question also. So the final expression is also important. It is not sufficient if you learn the derivation alone. The final expression alone should also be known by heart. So we will meet in the next video lecture. Thank you, students. Thank you very much.